could get from one end of the solar system to the other by driving. Because space is so huge, we're bringing it down to Earth by scaling the distances in our solar system down to the size of the continental United States and placing the planets along our route. It's a 3.6 billion mile road trip, shrunk down to under 3,000 miles. My name's Colonel Chris Hadfield. When I was 9 years old, I saw the impossible happen. And from that moment forward, I wanted to make the impossible happen for me and to turn myself into an astronaut.
We have booster ignition and liftoff of the Space Shuttle Endeavour.
I've been a mission specialist on a space shuttle, the commander of the International Space Station. All told, I've logged almost 4,000 hours in space. I've flown through it, I've walked in it, I've even sung in it. But now, I'm driving it. Our road trip across the solar system starts here on Long Island, New York. That's the sun off the northeast coast. It's 10,000 degrees Fahrenheit on the surface. That's like 40 times hotter than my NASA spacesuit was designed for. But I'm going somewhere a little bit cooler. On this journey, I'll be joined by some amazing people, riding shotgun and guiding my adventures. So it's time to pick up my first passenger. Come on in. How are you? How are you? It's world-renowned astrophysicist Michio Kaku of the City University of New York.
That's right. I've heard so much about you.
I've heard lots about you
You
as
serenade
well.
the masses from outer space, right?
And I've been watching all the stuff you've been doing from afar. I think it's nice to have a little look at the world and the universe together.
Grand tour of the solar system.
The first leg of my journey will take us through the inner solar system to Mars. Mars has always held a grip on my imagination. And we're getting tantalizingly close to the day when an astronaut will actually step down onto the red planet. But there are many other wonders along the road from the sun. Look, there it is. Mercury, the first planet from the sun. Mercury is an average of 36 million miles from the sun. But here in the Miniverse, it's just 24 miles down the road. It looks a little like the moon, which is a place I've always wanted to go.
Many people think that, well, being on Mercury is very similar to being on the moon. No. If you were an astronaut, the sun is this huge fireball lighting up the sky, dominating everything you see around you. It would be quite a hostile environment with the sun just literally staring you in the face.
Yeah.
And it's blisteringly hot on the surface. It's 800 degrees Fahrenheit.
Wow.
Imagine you being able to bake a pizza in your back porch without an oven. But Mercury also has some surprises. You realize that there's ice on Mercury?
Like water ice?
Water ice, right. It turns out if you go to the poles, the North Pole and the South Pole, and look at the bottom of craters where you have permanent shadows, we think there's evidence of water ice.
So even that close to the sun, there are places that are permanently in the dark.
That's right. This shocked a lot of scientists who have this image of Mercury being this hellhole.
Beyond Mercury, we chart a course for Venus. In the universe, it's about 31 million miles. which means in the miniverse, Venus is only about 20 miles away. Venus and the Earth are almost the same size. For a long time, astronomers thought Venus was a kind of twin sister to our planet, but apparently it's Earth's evil twin.
You know, when I was a kid, I read science fiction novels that said that astronauts of the future will vacation on Venus. They'll have tropical environments and swim in the oceans of Venus. Boy, were they wrong.
Tropical environments, I think that was a bit of an understatement.
Temperatures approach 900 degrees on the surface of Venus.
Hotter than Mercury.
Yeah, and it rains sulfuric acid,
Oh.
and the atmosphere is so thick, and the pressure is so great on the surface of Venus, it's like being half a mile underneath the water in the ocean.
So that's like being way, way underwater with the pressure of the water all around you.
Yeah, even submarines. Submarines will be crushed like an eggshell at that depth. You know, here on the planet Earth, we experience pressure on our skin 15 pounds per square inch of your skin. On Venus, it's 1,500 pounds of pressure per square inch.
So it's sort of like in a spaceship when the engine's light and you're crushed back in your chair, except it's crushing you from all directions, not just from one side.
Right. So if you're an astronaut walking on Venus, you'd be crushed like an eggshell. I make a great tour guide, huh?
Maybe not such a good salesman, though. I'm not sure. You should not be selling real estate on Venus.
I'm selling Mars, actually.
Ah, here we are.
Who would have thought that this jewel hanging there in the sky is bright because of sulfuric acid droplets?
And yet we've built spaceships that have made it all the way to the surface, right?
Just for a few minutes, and then they got fried.
So it's the hottest planet in the solar system, and sulfuric acid is raining from the sky.
That's right. So if I was a tour guide, I'd say, maybe we should skip Venus this year.
As we leave Venus, we're headed for the only planet I've actually orbited as an astronaut. And the inner planets are so close to each other that to get there, we still won't be leaving Long Island.
I think you're going to recognize our next destination.
It's terra firma. It's our home world.
Home sweet home.
Yeah. We take it for granted, right?
Yeah.
But most of the universe is quite hostile. All these planets that are blisteringly hot or freezing cold,
Yeah.
it's great to find one that's just right to
Just
have life
right.
on it.
And there's my old home away from home, the International Space Station. I spent 5 months there, taking in the view every single moment I could.
And look, you can also see the northern lights, the southern lights.
Beautiful. I've had the great privilege of seeing the aurora in a way only a handful of people have.
I was outside on a spacewalk. It was on the dark side of the Earth.
Of course, I was just by happenstance just outside doing a spacewalk.
I had my lights shut off, my eyes had adjusted to the darkness, and we went into the southern lights, the Aurora Australis. They were rippling between my legs and pouring by. They're mostly like green and red, as you've seen in the pictures, but in them you get all the little subtle colors as well. I couldn't convince myself that even though I knew it was real, it was just hard to somehow accept the fact that this amount of gorgeous, pulsating light and color could be a natural, real thing. It was one of the most magnificent experiences of my life. Plus, we're going 5 miles a second, so it's almost like if you watch the surf crashing on the shore, but then you're skimming through it on a board, so you get your own added speed, like a surfer on a wave. Makes it even more magnificent. It's just...
Well, gee, that's the title of your next book, Surfing on the Aurora.
Maybe you're a better travel agent than I thought. Surf the Aurora. I like it.
Well, I've left Earth before, and I'm doing it again. And this is a journey I've dreamed about many times. From Earth to Mars. A world that has the best chance of becoming humanity's next home. Even when Mars is closest to us in its orbit, traveling there in a spaceship will take between 6 and 9 months. In the Miniverse, it's just down the Brooklyn-Queens Expressway. Sounds like a quick trip, but in the Miniverse, we have to deal with rush hour.
So how soon do you think until it's not just robots going there, but people?
Well, you know, going to the moon was a piece of cake. 3 days.
There are
you're
people
on the
that would
moon.
disagree with you.
Everything's relative.
Yeah.
To go to Mars, let's face it, it takes months.
Yeah.
NASA's laid out a tentative timetable. We're talking about the 2030s, just to orbit around the red planet, and perhaps by 2040 actually landing on there.
Wow.
Unless, of course, private enterprise catches up, in which case we'll be on Mars even sooner.
Yeah.
Would you want to go to Mars?
Oh, absolutely. Yeah, in a heartbeat. I'd love to. The idea of that early exploration and discovery, that's what always has made my heart beat faster, yeah. If it were easy, I don't think I'd really want to go, but the challenge that makes it possible, to me, that is what really makes me want to go.
But for me, nah, I don't think so. First of all, being a physicist, I know the odds of success. 1% of the spacecraft will blow up and never reach Mars.
Sounds like physicists are pessimists to me.
No, realists, that's all, just realists.
But that means 99% of them make it, you know? I think Mars is worth the drive. So if I sign up to go to Mars, if I stick my hand up way high and get picked, what do you see as the biggest hazards between here and there? Is it getting hit by small meteorites? Is it the radiation?
I think it's all of the above,
Yeah.
especially radiation. Radiation from the sun, cosmic rays. Radiation causes premature aging. At best, your body will age faster than normal, and at worst, cancer.
You know, something else, having spent half a year in space, one of the beauties of being on the International Space Station is you got the world in your window all the time. But as soon as we turn tail to Earth, fire the engines, and start going to Mars, within a week or two, Earth is just a little dot, and you have nothing out the window for 6 months, 9 months, however long it takes. I think you can't play down the psychological effect of that.
Right. So my attitude is, let someone else get all the ticker tape parades.
Despite all the challenges, Mars pulls at my imagination. It's a place where humanity has long hoped to find the first signs of alien life.
For the most part, we see no evidence of life whatsoever. You know, some people think they see a face on Mars, and there's one formation that looks like Kermit the Frog, actually, on
I haven't
Mars.
seen the Kermit the Frog formation.
But they're optical illusions.
There's evidence of methane in the atmosphere, which can come from microorganisms, but doesn't have to. Traces of water might bubble up to the surface, but might be too salty to support life. But there's also water in the ice at the poles.
Journalists say follow the money. Physicists and astronomers say follow the water.
Follow the water.
Where there's water, there could be hydrocarbons, organic chemicals, and who knows, maybe even an alien form of DNA. Wow, you can really see Mars in its full glory. I mean, you can see why the ancients named it after Mars, the god of war, because it's so red.
Red like blood.
Or like rust.
Or like the bridge, right?
That's
Rusty,
right.
like the bridge.
Sometimes that rust in the soil gets kicked up by the Martian wind. So if I was standing on the surface, the sky would be pink, not blue.
You know what amazes me is to think that right now on Earth there are a few people in darkened rooms operating controls that are driving robots around on that planet right now. And that maybe not too long from now, people will have a chance to go all the way there actually in person.
There'd be many wonders to behold on the surface of Mars, but the one I want to see most is Olympus Mons. It's the biggest mountain on any planet in the solar system.
It would extend from here, New York City, all the way into Canada.
And how high?
It would be like, well, take 53 of those Freedom Towers going all the way up.
53 of those? Wow.
Yeah, imagine 53 of them stacked vertically on top of each other.
Wow, that's
53
go
of
out
them.
of sight, wouldn't it?
That's 16 miles high, 3 times taller than Mount Everest.
And you don't want to be the astronaut that plants the flag on the top of Olympus Mons there?
No, I'll let someone else have the glory. But that's the lure of Mars.
As I drive Michio back to his home in the city, I wonder what home would look like on Mars.
So instead of building a dome like in science fiction novels, why not use the volcano tubes that already exist? Tubes that once had liquid lava flowing through them can also be used as caves for the astronauts, protected from the cosmic rays, the solar flares, and the micrometeorites. That'd be the quick and dirty way to get a Mars base off the ground.
It was an absolute delight, Professor, to travel the inner solar system with you.
Right? It's been a cosmic tour through the universe.
Thanks. I look forward to seeing you somewhere else around the solar system.
We covered 141 million miles in the solar system without ever leaving New York. But that's about to change. Like a pioneer pushing into a vast, uncharted wilderness, I'm ready to leave the familiar surroundings of the inner solar system for the strange and mysterious realm of the outer planets.
In other words, I'm headed to Philadelphia.
In the inner solar system, we passed 4 planets in less than 100 miles. Things are going to get a lot more spaced out. In the universe, the average distance between the Sun and Mars is 141 million miles. Then, the average distance from Mars to Jupiter is 342 million miles. In the miniverse, that's like a trip from New York to Washington, D.C.
Whoa! Halfway between Mars and Jupiter, there's an enormous ring of rocks called the asteroid belt. That one just missed. Yikes. The asteroid belt has millions of small particles.
It also has about 750,000 bigger asteroids, some of them more than 3,000 feet across. Some people think that the asteroid belt looks like the world's most dangerous video game.
But in real life, there's an average of about 600,000 miles between each of the significant asteroids.
Even in the miniverse, that's about a quarter of a mile. Still, plenty of space to maneuver through safely. So I've made it to Philadelphia in one piece. As I head for the outer planets, I'll need a guide who really knows this part of the solar system.
Hey, come on aboard.
Why, thank you.
It is the chief astronomer and planetarium director of the Franklin Institute in Philadelphia, Mr. Derek Pitts.
You got
Welcome
it.
to my spaceship.
How are you, Chris? Thanks
I'm
a lot.
ready. Are you ready to head across the solar system with me?
I'm ready to take a trip through the planets.
All right. So we got some big planets coming. Glad to have you aboard.
I'm looking forward to it. This is the first time I've actually taken a trip through the outer solar system.
Well, this is the first time for everything. So the beauty of shrinking the whole solar system down to the size of the U.S. is you get through the asteroid belt fairly quickly.
We're on the road to Washington, D.C. Drawn in by the immense gravitational pull of the most massive planet in the solar system. Jupiter's almost 88,000 miles in diameter. That's 1,300 times bigger than Earth. You could actually fit Earth and all the other planets inside Jupiter and still have room.
And in fact, Jupiter itself weighs more than all the other planets of the solar system put together twice.
Wow. It's the heavyweight.
It is big.
Jupiter's huge, but even with all that mass, there's no place for an astronaut to put a footprint.
It's really just a big, big ball of gas.
Wow.
Hydrogen, helium, methane, ammonia.
Wow.
But as an astronaut, what would it look like to take my spacecraft and start diving down into Jupiter?
You'd have a very interesting trip as you descended down into the clouds of Jupiter. First of all, you'd start down into the cloud tops of maybe several thousand miles. You'd start to notice that you're losing sunlight and things are getting darker. But you'd begin to pick up lightning. You'd see flashes all around you.
If you get right to the very center of Jupiter, what's right there in the middle?
Well, oh my gosh, the pressure increases so much that gaseous hydrogen can be squished down until it becomes a liquid, and then it turns into something very interesting called liquid metallic hydrogen.
Liquid metallic hydrogen. That sounds like a science fiction movie.
I wish I could explain it, but I don't think I
You know
can
that
even
creature
tell you what
that
it's like.
drags himself up out of that
Out of
silver
the
liquid?
ooze and
That sounds like liquid metallic
I think
hydrogen
that's where
to me.
that guy came from.
Yeah,
Yeah,
sure.
well, in any case, right down in the middle of all this liquid metallic hydrogen, there might be a rocky core, a solid core inside that.
So if you get right to the core of Jupiter, I mean, what sort of pressure are you actually facing there?
All right, so the pressure at the core of Jupiter is about 30 million times the surface pressure here on the Earth.
So,
If you start at about 6 feet tall, by the time you get to the center of Jupiter, you're going to be about a half an inch tall. But you also have extremely high temperature down there as well. About 63,000 degrees Fahrenheit. About 6 times hotter than the surface of the sun. So if you're an astronaut going into this, you're going to have a beautiful light show for the first half of your trip. And then the next half of your trip is going to be like the worst horror show nightmare you've ever experienced.
wow. Yeah, I'm going to have to really rethink my my Jupiter spacesuit.
I think you might want to go with the space probe thing instead.
Yeah.
Okay, so maybe it's safer to let spacecraft like the Juno probe go inside Jupiter.
Great. Approaching Jupiter.
But to orbit Jupiter, to see it up close, would be one of the most amazing experiences in the solar system.
Whoa. Look at that, right above the... Holy cow.
You know, I knew it was big, Chris, but this is really incredible.
Look at the colors of that. That's amazing.
And look at the detail you
Yeah.
can see in the cloud tops.
Wow.
All the little whirlpools.
That's worth the trip.
It is definitely worth the trip.
It makes sense that Jupiter's over Washington, D.C. Washington's influence is felt all over the world, just like Jupiter's influence has been felt all across the solar system. Its gravitational pull is so strong, it acts like a cosmic vacuum cleaner, sucking in comets and asteroids that might otherwise rocket into the inner solar system and strike our planet. As an explorer, I'm often drawn to the things that frighten me the most. On Jupiter, it's the intense violence of the monstrous Great Red Spot.
Whoa. That's incredible. And the red spot right over here coming across this way.
It's a ferocious storm that may have been churning for 300 years.
It's really spectacular.
If I could orbit Jupiter at the same altitude that the space station orbits our planet, the Great Red Spot would fill my entire field of view. It's just that big, larger than the whole Earth.
That's a view and a half.
That really is amazing.
I flew through a lot of bad weather when I was a fighter pilot. I wonder what it would be like to drive through the Great Red Spot.
Are you serious?
Yeah.
That's an awfully dangerous thing to do.
The center is relatively calm, but as you near the outer edge, the winds climb to 400 miles per hour, twice as fast as the worst hurricane winds on Earth.
Okay. When you're flying through the Great Red Spot of Jupiter, remember, keep your windows up and your air conditioning on.
And that's because the red spot is full of ammonia and ammonium sulfite. Not good stuff.
Not good.
As we speed away from Jupiter, I'm reminded of the Cassini spacecraft that visited here in the year 2000. It sent back some unforgettable images before using Jupiter's gravity to slingshot towards its ultimate destination, Saturn. I've been lucky to see many spectacular sights in my time as an astronaut, but I've always thought that nothing would be more stunning than to see the rings of Saturn up close with my own eyes. It took the Cassini probe more than 3 years to make the trip from Jupiter to Saturn. But in the Miniverse, Saturn's just 6 hours away in West Virginia.
I got a bit of road to cover between now and then.
And it looks like we won't get to Saturn till after dark. Good thing we space explorers always pack snacks.
Well, look.
Look at
We
that.
got some astronaut ice cream.
Oh, my
How's
favorite.
that? Let's try some of this.
Can I have a piece?
Sure. Let me give you a
Hey,
hunk
it's-
there.
it's
There we go.
The attractive color you'd hope your space food would be.
Cheers. Cheers. It's not as bad as I thought it was going to be.
So I do have to fess up, though, we do not have astronaut ice cream on the space station. It tastes nice, but it's just too crumbly and not practical for weightlessness.
Right.
There's going to be stuff in your nose, in your eyes, in the computers.
This would be a mess everywhere.
Not bad for the Miniverse, though.
No, it's good for the Miniverse.
So let's just talk about the planet itself. You're an astronomer. What can I expect when I get to Saturn?
It's the rings.
It's got rings. That's
Everybody
right.
loves the rings.
Yeah.
All the gas giants have rings, but none of them can match Saturn's.
You're measuring about 176,000 miles across.
That's wide enough to line up 22 Earths side by side.
If you were flying your spaceship right next to the rings, what do you think it'd look like up close?
If you're right up close on it, it really would look like a very well organized rubble field because you have these particles of different sizes. You know, you're down to something that is dust sized and maybe up to objects that are the size of a small car or even a small house. But they're all in there together.
From just a little distance, the rings don't look like a rubble field at all.
Wow. Look right there.
That is spectacular.
Wow, you can see everything. You can see the colors and the delicate swirls and the rings.
The rings really are spectacular. Oh my gosh.
Saturn has dozens of moons, and at least 3 of them have underground oceans. Those are Dione, Enceladus, and Saturn's biggest moon, Titan. For a moon, Titan is pretty titanic. Even bigger than the planet Mercury.
Titan's really a wonderful place to visit too, because it's the one place in the solar system that we know of that has oceans on the surface.
Titan has oceans of what?
Ah, there's the catch. A lot of it is methane that's actually out on the surface, pooling in lakes. It also has a cloud cover that actually rains methane down onto the surface.
Wow, so methane rain.
At about 300 degrees below zero.
Oh, wow. So, you know, the suit that I wore for my spacewalks, I'm not sure that it could put up with the huge temperature extremes that we're seeing on the moons of Saturn.
You need something really special.
I don't think thick socks are going to help.
You need a little bit more than that.
You know, sleeping on a space station, you dream about views like this. When you close your eyes sleeping on a spaceship, sometimes you see flashes of light with your eyes closed. It's the radiation and the high energy particles from the universe that are going through your optic nerve and making your vision flash. It's a real reminder that you are somewhere other than Earth.
You don't see this on Earth, do you?
No, because our atmosphere soaks up the little particles that cause this to happen in our eyes. And I can imagine the first astronaut, the very first one who saw that, is probably going, I don't think I want to tell anybody. I'm seeing flashes when I close. I could see two astronauts going, hey, do you see flashes?
See anything like that? So
Well, yeah, oh, we all do. Oh, okay.
That's a really special experience.
It's part of what astronauts dream about.
I hate to leave, but I have more planets to visit. And Derek's got to get back to Philadelphia. Time to part ways.
Chris, it's been great.
It has been wonderful touring the solar system with you.
Thank you so much for taking me around. I've had a great time seeing all these planets so close.
I got a little bit more of the solar system to see, but thanks for being a tour guide
Well,
for
look,
me.
you have a really great trip.
Safe travels home, sir.
All right, Chris, take care now.
All right. Bye.
As for me, I need an early start. Because after Saturn, distances between planets get extreme. So there's no time to waste.
This is what's amazing. Our trip from here to the next planet is further than the entire trip so far, 900 million miles from Saturn to Uranus. The solar system is big.
In the miniverse, that puts Uranus hundreds of miles down the road, near Kansas City.
Gonna ride that lightning one more time. I'm gonna ride that lightning one more time. Gonna ride it one more time, 'cause there ain't no finish line. I'm gonna ride that lightning one more time. Gonna ride that lightning out of sight.
Out beyond Saturn, just like on the road through America's heartland, it can look pretty empty. Gives you a lot of time to think and look.
When I was a fighter pilot flying F-18s in the subarctic, I loved to take the airplane up as high as air traffic control would let me. And then I'd engage the autopilot, sort of like I could engage the cruise control in this car. And then I would shut off all the lights in the cockpit so that it was completely dark. And then I would let my eyes adjust. And you could start to see the stars as your eyes opened up. And for me, that was sort of an early taste of what spaceflight was going to be like, as close as I could get to the heavens, but almost no barrier at all between me and the rest of everything else. My first small step into space. If we were making this trip 300 years ago, it would have been in like a horse and carriage, we would have stopped at Saturn because, as far as everybody knew, that was the last planet. It was the furthest planet that we could see with the naked eye.
But there is another planet down that road in front of me. Another giant of gas and ice. Uranus. From a distance, it's hard to imagine the violence going on there. These Midwestern flatlands can get hit by 200-mile-an-hour tornadoes, but if I flew a spaceship into the clouds of Uranus, I'd be fighting winds up to 560 miles an hour. And as you get closer, you start to see something very strange. Uranus is lying on its side.
So if you were the Space Transportation Safety Inspector, you'd look at this and say, what the heck happened here?
Something in the early solar system, possibly some rogue planets, knocked this giant world over, rings and all. And that might not have been the most incredible thing to happen to Uranus. About 4 billion years ago, it was ripped out of its orbit. Gravitational interference from Jupiter and Saturn made Uranus switch places around the Sun with Neptune. That's like Kansas swapping locations with Colorado, but it happened. So today, Neptune is 1 billion miles out from Uranus, which puts the 8th planet in western Colorado. Like the pioneers of old, I've reached the Rocky Mountains. Ahead lies my final frontier. And here's my final co-pilot.
Hello.
Hello,
you
Commander
doing?
Hadfield. Nice to meet you.
It is great to meet Dr. Laura Danley, astronomer and curator of the Griffith Observatory in Los Angeles. Welcome to my spaceship.
Thank you.
We have the privilege of traveling a little bit of the solar system together.
I'm really looking forward to it.
Yeah,
We've
some
got
things
a
to...
long distance to travel.
Let's
go.
Seat belts,
All right.
engage.
So, Laura, as my spaceship enters into orbit around Neptune, what's the first thing I would notice?
Well, Neptune is blue, and there's nothing you can do.
That'd be a good song, wouldn't it?
That would. Maybe you could sing it later.
Looking down on Earth from the space station, you're struck by the incredible deep blueness of our planet. But the blue on Neptune isn't water. It's reflected light from methane in the atmosphere. And that atmosphere is roiled by the wildest winds in the whole solar system.
There are storms in the atmosphere that appear quite dark.
Like spinning storms?
Yeah,
or-
huge cyclones.
Huge cyclones.
And they are so violent that the wind speeds in those are about 1,500 miles an hour.
Like 1,500?
1,500
I mean,
miles
a
an hour.
category whatever hurricane, 200 miles an hour is wicked.
Yeah,
on the
this
Earth.
is a category
Wow.
25. It's
Wow.
way up there.
How big is the storm?
The big one is about the size of the whole Earth. You could fit a whole Earth in it. Yeah, it makes our storms look like kindergarten over here.
Earth-sized storms with winds 10 times faster than my top speed.
Wow, that's incredible.
Yes.
And look at that.
Well, here we are. Wow. What an amazing sight.
An astronaut visiting Neptune wouldn't want to leave orbit because there's nowhere to stand and plant your flag.
No, you can't be standing on it because it's gas mainly.
Sure.
So you would keep falling on through.
Whoa! Here's some solid ground. Neptune's largest moon, Triton.
Wow.
Triton is an amazing world. First of all, it's about 1,500 miles across.
Standing on Triton, what do I see? What's it look like?
Well, an icy surface everywhere. Mainly nitrogen, little methane, maybe a little CO2. If you're standing in the right place, you might also see kind of an orangey, rust-colored coating on it. These are hydrocarbons or organic molecules like methane and ethane that have been singed by ultraviolet light from the sun, and they fall down onto the surface like just a fine veneer on top. And if you were in the right place, then you may see a geyser of nitrogen ice spewing into space.
An ice geyser spewing up around me. Wow.
5 miles tall. Think about that compared to, say, Old Faithful.
Miles high.
Right.
Well, I want to go.
It's an amazing world.
Sounds like it'd be worth the trip.
Yeah.
Triton may have something special that makes it a target for future explorers. A warm subsurface ocean with the possibility of life. Think how amazing it would be to gaze from a scenic overlook on a distant world and see someone or something looking back at you. It's opportunities like this that
Not very many. 3. Shuttle's pretty low G vehicle.
Think you can get us 3G?
sure can. Warp factor 3.
So when you go beyond Neptune, is it like in Star Trek where there's all those things whizzing by, or is it empty?
It's for all intents and purposes empty. Lots of space.
So space is the right name.
Yes, it is. Lots of it. Space, comma, lots of it.
That pile of rubble.
I know.
It's like a Star Trek set,
It
doesn't it?
does.
Fighting the Gorn.
Why does everybody know about fighting the Gorn? That is like one of those memorable... The Gorn was such a wonderful monster.
From Earth, even the Hubble telescope can barely make Pluto out. That's because it's an average of 3.6 billion miles away.
If you were able to fly out there in the shuttle, it would take you about 20 years.
A long time with 7 people sharing one toilet. That'd be a while. Yeah.
And then if we were driving at 60 miles an hour, it would take us 6,700 years to get out there.
Wow.
So, yeah.
Are we there yet?
In 2006, while I was working at the Johnson Space Center, my NASA colleagues launched the New Horizons probe to get a closer look at Pluto. But while New Horizons was en route, Pluto was demoted from 9th planet to dwarf planet.
Kind of feel bad for Pluto. You know, it was part of the club for all that time, and we just kind of threw it out just because we changed our own standards. Well, how do you feel?
I have to say, I feel the same, which is why sometimes I mistakenly still call it a planet. It's just a force of habit, and it has a history.
In the summer of 2015, I was on the edge of my seat as the New Horizons probe sent back one mind-blowing picture after another. Suddenly, I could imagine myself walking on this distant world.
I think everyone thought it was just going to be an icy chunk out there.
Yeah, like an ice cube. out
Yeah,
there.
surpassed everyone's wildest imagination.
Turns out, if I went to Pluto, I'd find a world with a super thin atmosphere that, like Earth's, is mostly nitrogen. A world with mountains of solid ice, 11,000 feet high. And Pluto has an ice field about 1,000 miles across in the shape of a heart. And deep under its icy surface, a huge, warm, liquid ocean Nobody thought we'd be following the water to Pluto. We're
Cool car.
Very cool.
There's a mist rolling in from the Pacific Ocean, which gives me a very slight idea of what a day on Pluto would be like.
40 times farther away from the sun than the Earth.
So the sun shrunk down to almost nothing.
Shrunk down to just a bright star.
Really?
So it's not entirely dark, though. Sort of like it is around dusk here on Earth.
So where should we land? Should we land right in the middle of the heart?
You know, that wouldn't be a bad place to land because it's wide open.
You'd have a
through
nice
to the-
little smooth spot.
Yeah.
Good for skating.
I was just going to say, you're Canadian. Strap on your skates and head on out.
What sort of gravity does Pluto have?
It's just about 1/15
1/15.
of Earth's, and the moon is
Wow.
1/6.
So
So
if
you
you
could
weighed-
really jump high.
If you weigh 200 pounds on Earth, you're weighing like 12 pounds on Pluto.
Yeah.
Wow. Be pretty cool.
It would be very cool.
Actually, it'd be pretty cold.
Every day, we're closer to the time an astronaut from Earth looks out from the porthole of a spacecraft and sees
There it is, at long last.
Long voyage. Imagine having that in front of your naked eyes.
Still can't get over it has a heart on it.
It's just so poetically perfect.
It
huh?
is, it really is. It's a beautiful world.
And you know, to have been around the world so many times, you look at the world a lot, but it's when you turn and look what there's still on the other side, what's
Star. In the fall of 2003, it unleashed an eruption of energy equal to 200 billion hydrogen bombs, blasting a tidal wave of superheated charged particles at speeds of up to 6 million miles an hour. It was one of the largest solar storms ever recorded. And it was aimed at Earth.
They were some of the fastest, hottest, and strongest storms ever measured.
Assaulting the Earth, the sun's energy forced space station astronauts to take cover in their most sheltered compartments. Lights went out. Communication streams were cut. Airliners scrambled for safety.
This really was a hurricane of space storms.
Though no major damage was done, these storms were a stark reminder that we live at the constant mercy of the sun. It controls all aspects of our lives. Our climate, our food, our bodies.
We actually live inside the sun's atmosphere. We, along with all the other planets, are greatly influenced.
But is its influence changing?
It's actually growing more powerful.
Might we lose its protection from deadly cosmic rays?
At its boundary, where it's protecting us from the intergalactic winds, that boundary is actually shrinking a bit.
Will our technology-dependent society be able to handle another solar superstorm?
Sometimes these effects can be so severe that they're catastrophic.
And when will the next superstorm strike?
Three, two, one, go for drop.
Pegasus is away on the IBEX mission. All Pegasus.
Fall 2008.
Stage 1 ignition.
NASA launches IBEX, the Interstellar Boundary Explorer. Part of its mission is to study the effects the sun has on the furthest reaches of our solar system. IBEX joins the long list of human attempts to explain our star's impact on our solar system, our planet, and our lives.
The sun. The sun provides all of our light and heat. If it weren't for the sun, we wouldn't be alive.
We people are very interested in what goes around us. We like to understand our neighborhood. The sun in the universe is our street, our neighborhood.
The sun. We are actually affected by its moods. In fact, it's like the parent, and all the planets are the children that are affected by its moods.
We need to know how it's going to evolve and how the changes that are always happening in the sun affect us here on Earth.
The sun. If we want to understand
the universe and the stars that make up the universe, then it's important to study the one that's closest to us.
We've learned more about the sun in the past 40 or 50 years than in all of recorded history.
This golden age of exploration was kicked off by a unique mission that gave us close-up images of our sun from above our atmosphere.
Skylab, we're reading you loud and clear over the Vanguard for 8 minutes.
In 1973, Skylab became the first manned space station. It sent back images of the sun, clearer than anything taken from Earth.
The Skylab mission was one of the very first laboratories that was dedicated just for the research and study of the sun. In some ways, it's kind of the grandfather of the current missions today.
Right now, a fleet of about 20 space probes scan and study the sun in ways we never imagined, even 30 years ago. By studying the sun from the vantage of space, we can see it in a whole new light, using different light wavelengths, including X-ray and extreme ultraviolet. We can peel back its layers and begin to understand how and why the sun acts the way it does.
The different wavelengths mean different temperatures, and different structures are more visible in different wavelengths than in others.
Our robotic space probes never stop watching the sun. With their help, scientists are working out the big questions about our star, and we already know a lot. The sun is one of over 200 billion stars in our Milky Way galaxy, but it is our closest at 93 million miles away from Earth, almost the same distance as 4,000 trips around the globe. And despite that distance, its light only takes 8 minutes to reach Earth. It is only 4.5 billion years into its nearly 10 to 11 billion year lifespan. And though technically a medium-sized star called a dwarf, it is enormous, 900,000 miles across, and if hollowed out, 1.3 million Earth-sized planets could fit inside. The sun accounts for 99.8% of the mass in the solar system, and it weighs 300,000 times more than the Earth. It is made up almost entirely of a superheated form of electrified and magnetized gas called plasma. The sun packs enough gravitational pull to keep the planets from spinning off into space. And as Copernicus first suggested, it rules the center of our solar system with a gravitational iron fist.
Copernicus's model, in which he placed the sun in the middle of the solar system with all the planets going around it, instead of everything going around the Earth, was a giant paradigm shift. It meant that the sun is the most important thing in the solar system. It meant that we really should understand the sun.
Our sun, like all other stars in the universe, is made from the dust of stars that lived and died over billions of years, going all the way back to the Big Bang.
So our sun and our solar system is really the debris from many generations of stars.
The sun we see every day is the solar system's source of power. Deep in the center of our star, its core is superheated to 27 million degrees Fahrenheit and is the engine that drives it all.
Inside the sun's core, the process of fusion is occurring, and that fusion process is giving off light and particles.
Every second the sun shines, it releases the same amount of energy as 1 million H-bombs. The sun's light is made of particles called photons, born in the core, then propelled by convection currents through the radiative and convective zones of the sun. Eventually, they reach the volatile outer layers of our nearest star.
The sun's outer parts consist of 3 regions. There's the photosphere, or surface of the sun, and it's not really a hard surface like that of the Earth. The sun is gaseous throughout. And the temperature of the photosphere is around 10,000 degrees Fahrenheit.
Above the thin layer of the photosphere is another thin layer called the chromosphere. And the chromosphere is slightly hotter than the photosphere, which is counterintuitive because you would think that as you go away from the source of all the energy and heat, the core, that temperature would drop. But in fact, the temperature rises from the photosphere to the chromosphere. And it gets even hotter as you rise to the third layer of the atmosphere called the corona.
And then beyond the chromosphere is a large, tenuous, extended region, the corona, which is millions of degrees.
The sun produces a continuous outward flow of energy called the solar wind, Constantly blowing, it carries energy out into the solar system, extending our sun's reach 9.3 trillion miles, well beyond Pluto.
The space in between the planets and the space in the entire solar system is not an empty void, but it's full of these particles and it's full of these rays of light.
While the solar wind blows away from the sun, its gravity holds and pulls everything in. Take comets. All comets orbit the sun and can get pulled directly into the line of fire. Recently, scientists witnessed one of the sun's most dramatic outbursts, a coronal mass ejection, ripping the tail off a comet.
When it hit the comet, the tail was cut off like you took a knife, and the tail drifted away. And then it took a little more time for the comet to generate more gas and plasma and dust and create a tail. It tells us about how the solar wind moves in the solar system and how it can affect things.
The sun affects everything it touches, even us. To learn just how much, scientists sometimes rely on a remarkable cosmic coincidence. The lethal output of the sun has made studying it almost as difficult as understanding it. But scientists can get a good look at our nearest star thanks to a cosmic coincidence. A total eclipse of the sun.
A total solar eclipse occurs when, from our perspective, the moon is exactly aligned with the sun and blocks its photosphere. It's a glorious sight.
The solar eclipse is the most wonderful thing to see. It grows really dark by factors of thousands within seconds. And as it does become so dark, you can look up in the sky, you see the dark shadow coming from one direction, sweeping at you. It's really coming at thousands of miles an hour. So it's very impressive to see.
Humankind has marveled at the mysteries of the eclipse for millennia. Scientists have used it as an opportunity to see the sun's outer atmosphere, the enigmatic corona. One of the hottest regions of the sun, energy from the corona radiates out to the edge of the solar system.
The entire solar system actually sits in this outer corona of the sun. So this atmosphere of the sun is bathing all the planets.
The engineers who built the Solar and Heliospheric Observatory, or SOHO, installed an artificial eclipse into the space probe. Called a coronagraph, it does the same thing as a natural eclipse, blocking out the blinding rays of the sun, so scientists can try and answer an old question.
How does the solar corona get so hot? After all, the everyday surface of the sun, the photosphere, is only around 10,000 or a little more Fahrenheit. And the corona, on the other hand, is millions of degrees hot. If you go away from a stove, you know it gets cooler, but if you go away from the everyday surface of the sun, it gets hotter. And how is that?
It all starts at the sun's core, where every second, nearly 700 million tons of the universe's most common element, hydrogen, are converted into helium through nuclear fusion, giving off the energy that becomes photons, otherwise known as light.
The sun's core is really hot, several tens of millions of degrees. And there, the temperatures are so high that protons' hydrogen nuclei can come together, grab each other, fuse, eventually into helium, and in this way, release energy.
What happens with these photons, they go through this process, what we call a random walk, where they have to go through the layer of the sun, they get absorbed and then reabsorbed into lots of different photons at lower energy level. So this process of being absorbed and reabsorbed millions of times can take 150,000 years.
Once out of the sun's interior, photons are only 8 minutes away from Earth, but they're leaving behind a world in constant motion. The solar surface boils. Energy rises constantly from below. Coils of plasma and energy, called coronal loops, spring across the sun. While dark regions known as sunspots stretch thousands of miles, and at only 7,000 degrees Fahrenheit, these sunspots are the coolest part of the sun, emitting less light than the surrounding area.
If you were to pluck a sunspot away from the sun and place it in the sky, it would actually be as bright as the full moon.
Sunspots appear on the surface and are easy to see. Their genesis, however, is tied to the sun's deep interior and complex rotation.
The sun doesn't rotate like a solid body. Instead, it rotates more quickly near the equator than near the poles, which leads to sunspots. The equator completes one rotation in 25 days. Mid-latitudes complete one rotation in about 30 days, and near the poles, one rotation is completed in about 35 days.
Called differential rotation, this process makes the sun's interior churn at different speeds, creating intense magnetism in the form of millions of magnetic field lines, which get mixed up as the sun's interior twists up like a rubber band.
This builds up pressure, which makes them buoyant. So they float to the surface, and where they pop through the surface, they create sunspots.
Once on the surface, the now twisted and balled up magnetic field lines block the convection of superhot plasma from rising, making sunspots appear dark.
And when those sunspots start to twist around, you can imagine that you have one sunspot here and one sunspot here, and there's a magnetic field that connects the two. And that magnetic field gets twisted, and eventually the same sort of thing that happens with a rubber band, it pops. And when the magnetic field pops, it releases energy. And in the case of the sun and solar flares, it releases huge, huge amounts of energy.
The magnetic field lines created by the twisting and churning of sunspots, though invisible, can be seen in the dramatic formations on the surface of the sun, in the form of flares and prominences. It is here that the sun's influence starts, as the breaking of these magnetic field lines drives massive amounts of energy from our nearest star out into the solar system. And it is these magnetic field lines that are behind most theories on why the corona is so much hotter than the surface.
It's pretty clear that it has something to do with the magnetic field that heats the corona. But presumably there are waves along the magnetic field that bring energy from underneath the surface of the sun into the corona.
The solar probe Hinode, which means sunrise in Japanese, was launched in 2006. Its mission to study the interaction between magnetic field lines and the corona. Recently, it captured images of one of the waves thought responsible for heating this enigmatic region, Alfvén waves.
Alfvén waves are waves that occur in a plasma, in a bunch of ionized gas, threaded by a magnetic field. And indeed, it's thought that these Alfvén waves might be bringing turbulent energy from inside the sun out to the corona, where that energy heats the corona.
Energetic Alfvén waves form inside the sun and travel up through the surface, making the looping magnetic field lines sway and vibrate.
And so through this vibration or this oscillation, they're having friction with the magnetized plasma surrounding it in the corona. And through this friction, heating occurs.
It's this heat, delivered to the corona, that radiates out into space, filling our solar system with the sun's energy. But this energy is not constant. Our sun is an ephemeral body, never the same from one day or one year to the next. Like Earth changes with seasons, so does the sun. And when the solar seasons change, anything can happen. Day in and day out, the sun we see appears the same. But like Earth, the sun has seasons, solar minimum and solar maximum. Two distinct personalities that can affect our technology and possibly even our weather. The transition between solar minimums is called the solar cycle, an average 11-year period in which the sun's activity maxes out, then ebbs again.
The primary measure of the solar activity cycle is the number of sunspots visible on the sun.
During solar minimum, the period with the fewest sunspots, solar activity is limited. When sunspots break through the surface during solar max, the sun's power reaches out.
When there are lots of sunspots, there are lots of flares and coronal mass ejections.
Increases in solar activity enhance the connection between sun and Earth. Energy expelled from the sun can create disturbances in the near-Earth environment.
The Earth is embedded in the solar atmosphere, and so what happens on the sun affects the Earth, and that's what we call space weather.
Accurate space weather forecasting is the ultimate goal, but this can be hard. The sun is turbulent, especially during solar maximum, the peak of solar storm activity.
During solar maximum, the magnetic field of the corona becomes very complicated, and you have magnetic field everywhere, all around, even near the poles. You can have coronal mass ejections and flares and solar storms occurring sometimes several times a day.
Solar flares, violent eruptions of energy, usually near sunspots, burst into space. Like a bolt of lightning, quick and powerful, they can happen over a matter of minutes and can give off the same amount of energy as 1 billion megatons of dynamite.
Solar flares are gigantic outbursts of energy from the sun coming from a very small localized region of the sun's surface. So they're very concentrated ejections of energy that heat the surrounding gas to 10 million degrees.
Solar flare is sort of like a snapping of the whip. It really releases a lot of energy very quickly, accelerating particles almost up to the speed of light.
The particles from the very most energetic solar flares can reach us in something like 15 minutes.
But the solar hurricane of space weather comes from coronal mass ejections. These massive blasts carry billions of tons of superheated gas and plasma into interstellar space.
So coronal mass ejection is where a huge amount of mass and energy is expelled away from the solar surface. So if you can imagine this huge amount of mass and energy traveling away from the sun at these large speeds, sometimes at over 1 million miles an hour.
They throw these like big bubbles of hot gas and magnetic field. It can move off the sun so quickly that it actually creates a shock wave. They're the biggest storms, and they're the important ones for understanding space weather.
Solar probes, like SOHO, have captured the sun expelling massive amounts of energy into space. But scientists are most concerned when they see something called the halo effect, when the cloud of energy appears to surround the coronagraph. That means the sun has aimed its latest blast at us, like in the massive solar storms of 2003.
The fastest coronal mass ejection ever studied in modern times came from these storms.
Shortly after the initial blast from the sun, SOHO was bombarded by charged solar particles, protons and electrons, overwhelming the camera and causing the image to drop out.
What happens is you see a sort of snow on the camera, all sorts of sparkles going by, and that's the particles accelerated by the coronal mass ejection hitting the actual camera on SOHO.
If caught off guard, solar storms can harm astronauts, exposing them to the same amount of radiation in seconds that we receive on Earth in a year.
So if we're going to send astronauts back to the moon and to Mars, it becomes very important to be able to determine when these coronal mass ejections and storms are going to occur. The charged particles embedded in these coronal mass ejections are dangerous. It's a lot of radiation that would hit an astronaut.
Astronauts and satellites aren't the only potential victims of solar storms. The particles blasted towards Earth can interact with our magnetic field, occasionally wreaking havoc.
When this material comes smashing into the Earth's magnetic field, it causes it to ring almost like a bell. And when you have a magnetic field and when that magnetic field moves, physics tells us it's going to create currents. And so electrical currents will be created in the outer atmosphere of the Earth. And these electrical currents can cause all sorts of disturbances.
The currents create problems for satellites orbiting the Earth. They disrupt global positioning systems. They can interfere with communications equipment, causing radio blackouts and knocking out mobile phone systems.
These mass ejections can send so many charged particles toward the Earth that some of them make it through the Earth's magnetic field and even reach power stations here on Earth, causing surges of electrons and power outages and short circuits and things like that.
In extreme situations, solar storms cause excessive radio interference and increased levels of radiation, requiring planes flying near the poles to be rerouted. But as powerful as the storms were in 2003, they're no match for what astronomer Richard Carrington saw in 1859, a super flare.
The super flare of 1859 was incredible because prior to this event, we didn't even know that flares existed. Carrington saw this huge bright flash on the sun with the unaided eye, and in order for him to see that, it had to have been a super huge flare.
There were reports of telegraph lines running without being powered.
We probably won't see another one that intense in our lifetime, although it's hard to say for sure. The sun has thrown us some surprises.
If a similar storm were to strike today, one recent estimate projects 130 million people would lose power, possibly for months.
Most of the electrical infrastructure, the power grids around the world would be knocked out. A lot of the transformers would be overloaded. Having a large portion of the population with no power for many, many months could cost huge amounts of money. People have estimated that it would be upwards of $2 trillion.
We won't know unless it actually happens, and the more warning we get, the more we can do to reduce the economic impact, which is one of the reasons why we're studying the sun.
Scientists are a step closer to being able to predict these storms since the launch of the Solar Terrestrial Relations Observatory, also known as STEREO. This pair of probes now gives scientists the ability to see the sun in 3D.
So now, when one of these coronal mass ejections travels towards us, we're actually looking at the side view. And so we can see how fast they're traveling, we can see how they're evolving, the structure.
In 2011, the STEREO probes will reach their ideal vantage point, opposite sides of the sun, giving NASA a 360-degree view, allowing them to see what is coming from the far side of the sun before it impacts Earth.
And so for the first time, we're going to have a complete view of the sun all the way around. So this is going to allow us to see everything that's happening on the sun at the same time, and this will lead us again into a better ability to predict these types of storms.
But as dangerous as solar maximum can be for its increase in space weather, the sun's solar cycle counterpart and calmer period, solar minimum, may come with its own dangers.
When there are a low number of sunspots on the sun, the climate here on Earth can actually cool a little bit.
2008 saw the fewest number of sunspots in nearly a century, with a total of 266 sunspot-free days.
In 2008, we were at sunspot minimum, but by now we expected to be climbing out of that sunspot minimum, and we're not. So this could mean that this particular sunspot minimum is more protracted.
Scientists believe that past protracted minimums have had a chilling impact here on Earth.
Now, every once in a while, the sunspot activity cycle seems to just go away or become much diminished. There was such a period around 1650 to the early 1700s.
There were only about 50 sunspots recorded, when normally in the same time frame there are tens of thousands. So it was a really low period of sunspots.
It was called the Maunder minimum. The sun was in a quiet state. And that was associated with lower than normal temperatures here on Earth. Europe experienced sort of a mini ice age during those few decades.
Whether or not this current minimum will be protracted enough to have such a large impact on Earth won't be known for years. But another measure of solar activity, the solar wind, appears to be waning. And that could impact Earth tomorrow. Bathed in the sun's atmosphere, Earth is shielded from deadly cosmic rays. And while the sun's power protects us, it can also harm us. Life on Earth survives this close to its star, thanks in part to its ozone layer. But what would happen if the ozone layer were gone?
If Earth lost much of its ozone layer, ultraviolet radiation from the sun would penetrate through the atmosphere and reach the Earth's surface.
The sun's massive amounts of ultraviolet rays would quickly eliminate most basic elements of the food chain, wiping out plants and then animals.
If we are bathed in huge amounts of ultraviolet light, eventually the life on the Earth would die.
But what could cause such a catastrophic collapse of the ozone layer? Something the sun is supposed to protect us from: a gamma ray burst.
Gamma ray bursts are intense, brief flashes of the most energetic kind of radiation known, gamma rays.
The most powerful events in the universe. In seconds, they give off the same amount of energy that the sun will emit in its entire life. They occur when certain large mass stars die or even collide.
They can be generated from very extreme processes, such as large mass stars collapsing into black holes.
They occur somewhere in the sky roughly once per day, and they come from very, very far away. Most of them are billions of light years away.
But just 8,000 light years away, deep within the Sagittarius constellation, buried in a pinwheel-like formation, looms a potentially ticking time bomb. WR-104. 2 stars locked in a cosmic dance, spinning a full rotation once every 8 months. But one of these stars is on the verge of going supernova and emitting a gamma-ray burst.
Now, one of these 2 stars is a very massive star that might someday form a gamma-ray burst, and its beam might hit the Earth. If the high-energy beam from a gamma-ray burst were pointing directly at the Earth, it could spell real danger.
The radiation from the gamma-ray burst would be so intense, very short, on the order of 10, 20 seconds, but this would set up a chain of events which eventually would deplete the Earth of maybe 50 or more % of the ozone layer.
Scientists have speculated that a nearby gamma-ray burst caused an ancient extinction on Earth millions of years ago.
At the time, there was only sea life that existed. And even though the sea life deep beneath the sea wouldn't be directly affected by the UV radiation, the plankton and the life near the surface would die off, and therefore the food chain would be affected.
The threat is heightened even further by something scientists have witnessed over the past few decades: a 20% decrease in the power of the sun's solar winds.
The solar wind is the steady emission of particles from the sun.
They carry the magnetic field that is in the solar corona out into space.
It exists even when there are no coronal mass ejections or solar flares.
The solar wind continues way out beyond the orbit of Pluto and has actually blown a bubble in interstellar space.
Now, that's a bit of a protective bubble because the magnetic fields protect us from charged particles coming from outside.
Normally, solar winds stream off the sun in all directions at speeds of 1 million miles per hour. Pulling the sun's invisible magnetic field along with it, they form the solar system's defense against intergalactic intrusion, the heliosphere.
The heliosphere is the very boundary where the solar wind hits intergalactic space. So it's this shell that's surrounding the sun and the solar system where it protects us from intergalactic winds here on Earth.
Recently, scientists have learned that the heliosphere is shrinking and getting weaker.
The solar wind pressure has been measured to be decreasing over the last 25 years. In fact, the heliosphere, where the solar wind pressure is extending out to, has actually shrunk a bit.
A weaker heliosphere increases the possibility that Earth will be exposed to harm from intergalactic cosmic materials.
So if there's less solar wind, then the heliosphere itself is going to shrink. That makes it easier for more cosmic rays to enter into the solar system.
Already, the amount of high-energy electrons, a small but telling aspect of cosmic rays around Earth, has jumped in number by 20%.
Looks like the cosmic ray electrons have increased, and you would expect that. If the solar wind has decreased by 20–30% over the last 15 years, the bubble will have gotten smaller, and you expect an increase in galactic cosmic rays.
The good thing for us is that we live on a planet with a thick atmosphere and a magnetic field. So we have 2 types of shields that protect us.
But that could change when WR-104 emits its gamma-ray burst, possibly upsetting the balance of Sun and Earth, a balance that may already be in jeopardy because of something the Sun did billions of years ago. Over billions of years, the Sun and the Earth have developed the perfect balance for life to thrive. Sitting in the Goldilocks position of the solar system, not too hot and not too cold, the Sun gives us just enough light, just enough heat, and just enough energy to fuel our planet and our lives.
The sun drives everything on the Earth. The sun is the energy source of the Earth. So all of the energy that's given off by the sun heats up the Earth. This drives weather. On a larger time scale, this drives climate. So basically the sun is the energy source. It's the battery that drives the whole Earth environment.
Plants harness the sun's energy through photosynthesis, creating carbohydrates. People and animals consume these carbohydrates, converting them into energy we can use. Even the fossil fuels that power our lives were created by the sun. But our increased use of fossil fuels seems to be upsetting the balance between the sun and the earth.
Since all living material gets its energy initially from the sun is the source of the fossil fuels, whether it's trees, whether it's other things that have been trapped in the rock layer and then squeezed and slowly over millions of years made into the hydrocarbons that we know them as. And we then harvest and use those from underground.
The fossil fuels that we burn today unleash the sun's energy from millions of years ago, overwhelming the balance struck between our planet and its nearest star.
If we burn all this, we will have changed the atmosphere unrecognizably long before we get to a point when we're actually running out of the resource itself.
Already, we have seen the effects of too much solar energy in the rise of global temperatures. The release of millions of tons of ancient solar energy stored in fossil fuels has amplified the necessary and natural process called the greenhouse effect.
Many people think that the greenhouse effect is a bad thing. Well, in fact, it's not. It keeps the Earth warm. Without the greenhouse effect, Earth's oceans would be frozen solid. What is bad is too much of a greenhouse effect. If there's too much carbon dioxide and water vapor and methane in the Earth's atmosphere, then those gases trap too much of the sun's radiation, elevating Earth's average temperature, leading to global warming. Now that can cause a melting of the polar caps and a rise in the ocean levels, leading to just a calamity on Earth if it happens too quickly.
Not only will our atmosphere continue to trap more heat, it could start to decay. Continued use of fossilized solar energy will allow in undesirable amounts of radiation from our sun. Right now, our ozone layer prevents the majority of the sun's ultraviolet radiation from reaching Earth, while allowing just enough sunlight to give us what we need to survive.
Sunlight interacting with our skin produces vitamin D, which is a very useful vitamin.
Vitamin D can protect us from a number of diseases, including the bone disorder osteoporosis and heart disease. But here, too, a balance has been struck. Too much sun can alter our DNA, causing skin cancer. Maintaining the equilibrium between sun and earth that allows life to thrive will require using less of the sun's ancient energy and more of the energy it delivers on a daily basis. After all, the sun's energy output is estimated to be 386 billion megawatts. Meaning in 15 minutes, our star radiates as much energy as all life on Earth consumes in 1 year. Tapping this power source has been the goal of scientists for decades.
For sheer size, a solar satellite would be unprecedented. A structure 35 to 40 square miles covered with solar cells, able to capture the sun's energy 24 hours a day and beam it to Earth.
NASA has yet to achieve a goal on that scale, but their work with solar technologies in space has advanced technology here on Earth.
History of solar cells is essentially a technology that came back down to Earth from space. When we first started to work on the Apollo and Mercury and Gemini programs, we needed power plants in space. Solar cells were a natural way to do that.
Currently, we have two ways of directly harnessing the sun's energy. Solar thermal, which converts the sun's energy into heat by concentrating it enough to drive turbines, and solar panels, which use silicon-based technology to directly convert the energy from above into electricity. We can indirectly tap into the sun's power through wind turbines, capturing the energy produced by the weather the sun helps create. These technologies are constantly being improved. But some of the most interesting new science is coming from a very old process, photosynthesis.
There's some really exciting opportunities as we move from the world of semiconductor solar cells to organic ones.
Attempting to mimic Mother Nature, scientists have been able to create electricity from something found at the farmer's market, spinach.
There's organic molecules in spinach, in all green plants, but spinach happens to have a very convenient one, where you can harvest that peptide, that molecule.
Researchers were then able to put that peptide into a kind of solar sandwich, placing it between two electrically conductive materials.
And when it's exposed to sunlight, it will circulate electrons, which is current, which is electricity. So these organic molecules can actually become little solar cells.
In order to maintain the balance between Earth and our nearest star, it's become clear we must focus on finding ways to fuel our lives with the energy the sun supplies today. After all, the promise of solar energy is that for as long as the sun shines, its power can be ours. But what will happen when its power becomes too plentiful? The elements that make up the sun, the earth, and even humankind all come from one place, stardust, the remains of stars that lived billions of years ago. And just as those stars died, so too will our sun.
In about 5 billion years, the sun will pretty rapidly become much more powerful, much brighter, and much bigger.
The sun will reach a stage where it has burned through all of its hydrogen. And once that happens, it will start to burn through all of its helium.
The sun will start to expand as it reaches a stage called a red giant. As it expands, it will start to expand into much larger size and fill the inner solar system.
The orbits of the planets themselves will actually expand outward as well, because it's not as massive.
During that stage, some instabilities, which I call cosmic burps, will cause the sun's outer atmosphere to be gently ejected.
The outer layers of the red giant will just keep drifting off at some slow rate.
The hot inner layers of the sun will ionize that cloud of gas surrounding it and cause it to glow. So our sun will be surrounded by these glowing clouds of gas.
They will form what's called a planetary nebulae. They're beautiful shapes. Some are just purely round, but some have been distorted into other shapes. They've come off non-symmetrically from the star underneath.
What'll remain is the contracting core of our sun, and it won't produce any new energy through nuclear reactions, because all the nuclear reactions will have stopped. So it'll continue contracting and slowly fading with time.
It's very similar to the process that creates, say, supernova, but our sun is not big enough, doesn't have enough stuff to actually create a supernova. So its final stage will be this object we call a white dwarf star.
What remains is this little, relatively small white dwarf star, and it is a very quiet, what we call happily retired star.
It'll be about the size of the Earth, it won't get any smaller, and it'll sit around as this very highly compressed rock forever. It'll just liberate its energy, growing ever colder and dimmer with time, until finally it just fades from view.
The death of the sun will have catastrophic effects on the solar system. If the massive expansion doesn't swallow the nearby planets, it will likely change their orbits and superheat them, including Earth.
Earth's surface will be fried to a crisp.
The Earth is probably going to get baked one way or the other.
I mean, imagine the sun being 100 or 200 times brighter than it is right now. Imagine how much the Earth would be heated. It would not be a pleasant place to be.
It actually may get baked before the sun completely dies, because the sun will get hotter even before it becomes a red giant and gets as large as the orbit of the Earth. It'll get warmer, and at some point the Earth will get hot enough so that water will boil.
So the oceans will evaporate away, and all of life as we know it will cease to exist.
If there's anything left of the Earth, the sun will shrink down to a white dwarf, and the Earth will, instead of heating, freeze.
This will not be a pleasant place to live.
But that's billions and billions of years from now. We've only had rockets in space, satellites, for 50 years or so. Now we're talking billions. So clearly we'll be able to travel around the solar system at the very least, to go to places that will be at the temperature that the Earth is now, and we'll be able by that time to go to more distant solar systems. So I don't spend a lot of time worrying about what's going to happen to the sun in 5 billion years.
The sun gave us our life, and it will eventually take it away. And though the Earth will die, it and everything on it will in some part live on. The stardust that gave Earth and all of its inhabitants life will one day be
in a great cosmic pinball game we call our universe. How does energy stitch the cosmos together? And how do we fit within it? We now climb the power scales of the universe. From atoms, nearly frozen to stillness, to Earth's largest explosions, From stars, colliding, exploding, to distant realms so strange and violent, they challenge our imaginations. Where will we find the most powerful objects in the universe? Today, energy is very much on our minds as we search for ways to power our civilization and serve the needs of our citizens. But what is energy? Where does it come from? And where do we stand within the great power streams that shape time and space? Energy comes from a Greek word for activity or working. In physics, it's simply the property or the state of anything in our universe that allows it to do work. Whether it's thermal, kinetic, electromagnetic, chemical, or gravitational. The 19th century German scientist Hermann von Helmholtz found that all forms of energy are equivalent, that one form can be transformed into any other. The laws of physics say that in a closed system, such as our universe, energy is conserved. It may be converted, concentrated, or dissipated, but it's never lost. James Prescott Joule built an apparatus that demonstrated this principle. It had a weight that descended into water and caused a paddle to rotate. He showed that the gravitational energy lost by the weight is equivalent to heat gained by the water from friction with the paddle. That led to one of several basic energy yardsticks, called a joule. It's the amount needed to lift an apple weighing 100 grams 1 meter against the pull of Earth's gravity. In case you were wondering, it takes about 100 joules to send a tweet. So tweeted a tech from Twitter. The metabolism of an average-sized person going about their day generates about 100 joules a second, or 100 watts, the equivalent of a 100-watt light bulb. In vigorous exercise, the power output of the body goes up by a factor of 10, 1 order of magnitude, to around 1,000 joules per second, or 1,000 watts. In a series of leaps by additional factors of 10, we can explore the full energy spectrum of the universe. So far, the coldest place observed in nature is the Boomerang Nebula. Here, a dying star ejected its outer layers into space at 600,000 kilometers per hour. As the expanding clouds of gas became more diffuse, they cooled so dramatically that their molecules fell to just 1 degree above absolute zero, the total absence of heat. That's around 1 billion trillionths of a joule. That makes the signal sent by the Galileo spacecraft as it flew around Jupiter seem positively hot. By the time it reached Earth, its radio signal was down to 10 billion billionths of a watt. Now jump all the way to 150 billionths of a watt. That's the amount of power entering the human eye from a pair of 50-watt car headlamps a kilometer away. Moving up a full 7 powers of 10, moonlight striking a human face adds up to 300 thousandths of a watt. That's roughly equivalent to a cricket's chirp. From there, it's a mere 5 powers of 10 to the low wattage world of everyday human technologies. Put 10 100-watt bulbs together. At 1,000 joules per second, 1,000 watts. That roughly equals the energy of sunlight striking a square meter of Earth's surface at noon on a clear day. Gather 200 bulbs. 20,000 watts is the energy output of an automobile. A diesel locomotive, 5 million watts. An advanced jet fighter, 75 million watts. An aircraft carrier, almost 200 million watts. The most powerful human technologies today function in the range of 1 billion to 10 billion watts, including large hydroelectric or nuclear power plants. At the upper end of human technologies was the awesome first stage of a Saturn V rocket. In 5 separate engines, it consumed 15 tons of fuel per second to generate 190 billion watts of power. How much power can humanity marshal? And how much do we need? Long before the launch of the space age, visionaries began to imagine what it would take to advance into the community of galactic civilizations. In the 1960s, the Soviet scientist Nikolai Kardashev speculated that a Level 1 civilization would acquire the technology needed to harness all the power available on a planet like Earth. According to one calculation, we are 0.16% of the way there. This is based on British Petroleum's estimate of total world oil consumption, some 11 billion tons in 2007. Humans today generate about 2.5 trillion watts of electrical power. How does that stack up to the power generated by planet Earth? Deep inside our planet, the radioactive decay of elements such as uranium and thorium generates 44 trillion watts of power. As this heat rises to the surface, it drives the movement of Earth's crustal plates and powers volcanoes. Remarkably, that's just a fraction of the energy released by a large hurricane in the form of rain. At the storm's peak, it can rise to 600 trillion watts. A hurricane draws upon solar heat collected in tropical oceans in the summer. You have to jump another power of 10 to reach the estimated total heat flowing through Earth's atmosphere and oceans from the equator to the poles. And another 2 to get the power received by the Earth from the Sun at 174 quadrillion watts. Believe it or not, there's one human technology that has exceeded this level. The AN-602 hydrogen bomb was detonated by the Soviet Union on October 30th, 1961. it unleashed some 1,400 times the combined power of the Nagasaki and Hiroshima bombs. With a blast yield of up to 57 million tons of TNT, it generated 5.3 trillion watts, if only for a tiny fraction of a second. That's 5.3 yottawatts, a term that will come in handy as we now begin to ascend the power scales of the universe.
Of Discovery, a tribute to the dedication, hard work, and pride
To Nikolai Kardashev, a Level 2 civilization would achieve a constant energy output 80 times higher than the Russian superbomb. That's equivalent to the total luminosity of our Sun, a medium-sized star that emits 375 yottawatts. However, in the grand scheme of things, our Sun is but a cold spark in a hot universe. Look up into southern skies, and you'll see the Large Magellanic Cloud, a satellite galaxy of our Milky Way. Deep within is the brightest star yet discovered. R136A1 is 10 million times brighter than the Sun. Now, if that star happened to go supernova, at its peak, it would blast out photons with a luminosity of around 500 billion yottawatts. To advance to a Level 3 civilization, you have to marshal the power of an entire galaxy. The Milky Way, with about 200 billion stars, has an estimated total luminosity of 3 trillion yottawatts. A 3 followed by 36 zeros. The author Isaac Asimov imagined a galaxy-scale civilization in his Foundation series. Galaxia, he called it, is a superorganism that surpasses time and space to draw upon all the matter and energy in a galaxy. But who's to say that's the upper limit for civilizations? To boldly go beyond Level 3, a civilization would need to marshal the power of a quasar. A quasar is about 1,000 times brighter than our galaxy. Here is where cosmic power production enters a whole new realm, based on the physics of extreme gravity. It was Isaac Newton who first defined gravity as the force that pulls the apple down and holds the Earth in orbit around the Sun. Albert Einstein redefined it in his famous general theory of relativity. Gravity isn't simply the attraction of objects like stars and planets, he said, but a distortion of space and time, what he called space-time. How a totally dark object can do this has been narrowed by decades of observations and theory. If a black hole spins, it can turn into a violent cosmic tornado. Gas and stars begin to flow in along a rapidly rotating disk. The spinning motion of this so-called accretion disk generates magnetic fields that twist up and around. These fields can channel some of the inflowing matter out into a pair of high-energy beams, or jets. Gas and dust nearby catch the brunt of this energy, growing hot and bright enough to be seen billions of light-years away. Amazingly, the power of a black hole can rise to even greater extremes at the moment of its birth. As a giant star ages, heavy elements like iron gradually build up in its core. As its gravity grows more intense, the star begins to shrink until it reaches a critical threshold. Its core literally collapses in on itself. That causes the star to explode in a supernova. And now, in death, the star can unleash gravity's true fury. In the violence of the star's death, gravity can cause its massive core to collapse to a point, forming a black hole. In some rare cases, the newborn monster powers a jet that accelerates to within a tiny fraction of the speed of light. For a few minutes, these so-called gamma-ray bursts are known to be the brightest events since the Big Bang. 3 orders of magnitude above a quasar, at a billion yottawatts, a 10 with 42 zeros. Remarkably, they are still not the most powerful events known. Albert Einstein's equations contained an astonishing prediction: that when massive bodies accelerate or whip around each other, they can stir up the normally smooth fabric of space-time. They produce a series of waves that move outward, like ripples on a pond. Scientists are now hoping to detect these gravitational waves and verify Einstein's prediction using precision lasers and some of the most perfect large-scale vacuums ever created. At the Laser Interferometry Gravitational Wave Observatory, known as LIGO, they are hoping to record the collision of ultra-dense remnants of dead stars known as neutron stars and of black holes. According to computer simulations, as 2 black holes spiral into a fateful embrace, the energy carried by each gravity wave rises 5 orders of magnitude above a gamma-ray burst, to 100 billion trillion times the power of our Sun. Does the collision of black holes define the known power limits of our universe? Perhaps not. As turbulent as the environment of a black hole might be, its true power may well lie deep in its core. A black hole's mass is enshrouded within a dark sphere called the event horizon. Since the 1920s, scientists have described the mathematics of the event horizon as the equivalent of a waterfall. It's the point of no return, beyond which water falls freely into the gorge. At the event horizon of a black hole, space itself falls freely in at the speed of light. If the black hole is spinning, then the flow spirals down and around an inner horizon that envelops the singularity. That's the central region where space-time becomes infinitely warped. Any matter that rides this river of space whips around the inner horizon so fast that centrifugal force tends to fling it back out. As that happens, it collides with matter that's streaming in, whipping up a ferocious cosmic storm. The energy of the colliding stream feeds upon itself, rising to what may well be a limit imposed by nature. It dissipates only as it falls into the singularity and disappears. Fortunately for us, gravity walls off such energy extremes behind the event horizon, where they cannot affect the rest of the universe. And so, here we sit. Our world is nestled within a vast stream of cosmic energy, somewhere between the spin of an electron and the maelstrom of a black hole. There's no telling whether a future Earth civilization will be able to harness enough energy to advance into the cosmos. For now, as we tap into the tiny morsels of power at our disposal, we venture a closer look at a universe blazing with activity. We are its product, and its starstruck admirer. Lurking within dense star clusters, or wandering the dust lanes of the galaxy, where they prey on stars, or swallow planets whole. Our Milky Way may harbor millions of black holes, the ultra-dense remnants of dead stars. But now, in the universe far beyond our galaxy, there's evidence of something far more ominous. A breed of black holes that has reached incomprehensible size and destructive power. Just how large and violent and strange can they get? A new era in astronomy has revealed a universe long hidden to us. High-tech instruments sent into space have been tuned to sense high-energy forms of light, X-rays and gamma rays that are invisible to our eyes and do not penetrate our atmosphere. On the ground, precision telescopes are equipped with technologies that allow them to cancel out the blurring effects of the atmosphere. They are peering into the far reaches of the universe and into distant cauldrons of light and energy. In some distant galaxies, astronomers are now finding evidence that space and time are being shattered by eruptions so vast they boggle the mind. We are just beginning to understand the impact these outbursts have had on the universe, on the shapes of galaxies, the spread of elements that make up stars and planets, and ultimately, the very existence of Earth. The discovery of what causes these eruptions has led to a new understanding of cosmic history. Back in 1995, the Hubble Space Telescope was enlisted to begin filling in the details of that history. Astronomers selected tiny regions in the sky between the stars. For days at a time, they focused Hubble's gaze on remote regions of the universe. These Hubble Deep Field images offered incredibly clear views of the cosmos in its infancy. What drew astronomers' attention were the tiniest galaxies, covering only a few pixels on Hubble's detector. Most of them do not have the grand spiral or elliptical shapes of large galaxies we see close to us today. Instead, they are irregular, scrappy collections of stars. The Hubble Deep Field confirmed a long-standing idea that the universe must have evolved in a series of building blocks, with small galaxies gradually merging and assembling into larger ones. You can see evidence of this pattern by looking out into the universe. Many galaxies are gyrating around one another. Some are crashing together, others ripping each other apart. Gravity calls the tune as these galaxies draw together, exchanging stars and gas, and over time, merging to form larger composite galaxies. This came to be known as the hierarchical picture of cosmic history, in which the universe evolved from the ground up, with its structures growing larger and larger over time. A team operating at the Subaru Observatory atop Hawaii's Mauna Kea volcano examined one of the deepest galaxies known, whose light has taken nearly 13 billion years to reach us. It was a messenger from a time not long after the universe was born. This object is known as a quasar, short for quasi-stellar radio source. A small region in its center is so bright that astronomers believe its light is coming not from a collection of stars, but from a single object of at least 1 billion times the mass of our Sun. This beacon is generated by gas falling onto the object and heating up to extreme temperatures. The only thing known to generate this much power is a swirling cauldron where space suddenly turns dark as it merges into a giant black hole. For astronomers, the question was, how did this black hole get so big so early in the history of the universe? It likely got its start in an early generation of stars, often known as population 3 stars. Made up of hydrogen, they are thought to have been hundreds of times the mass of the Sun. These giant stars burned hot and fast and died young. A star is like a cosmic pressure cooker. In its core, the crush of gravity produces such intense heat at the moment the star dies, if enough matter falls into its core, it can collapse to a point, forming a black hole. The first generations of stars and black holes burst onto the cosmic scene in a time of incredible turbulence. Within primordial gas clouds, stars were being born in dense knots. They gave rise to black holes that began to swallow more and more matter. A computer simulation of the early universe shows just how quickly these voracious monsters were able to grow. The project, by scientists at Carnegie Mellon University, was designed to recreate a region in the early universe that measured over 100 million light-years on a side. It shows what took place in the first 1 billion years of cosmic history. This virtual universe is set in motion by equations describing the properties of gas, the energy released in starbirth, and the outward motion of time and space. The result? An intricate cosmic web, with gravity drawing matter into filaments and knots, like a vast tangle of interconnected spiders' webs. Inside the densest regions is where the largest galaxies and black holes grew. Here, circles indicate the appearance of black holes deep in the data. As they gain weight by eating up their surroundings, the circles grow larger. A few in the largest galaxies reach ultra-massive proportions, billions of times the mass of the Sun. These black holes were not just swallowing gas. The orbiting Chandra X-ray Observatory was dispatched to look into distant galaxies for black holes on growth spurts. Scientists looked for pockets of gas and stars glowing hotly in X-ray light. What Chandra found was that the core of some distant galaxies contained hot pairs, twin supermassive black holes drawn together by gravity. Black holes by nature resist this dark marriage. As the two approach each other, they go into an orbit that could last virtually forever. To learn what allows them to merge, we go back to the ideas developed by Albert Einstein. He said that when massive bodies accelerate or whip around each other, they literally disturb the fabric of space, causing it to ripple like a disturbance on a pond. When these ripples move outward, they carry with them the energy of the pair's orbit, causing them to spiral closer. When this dance of death comes to an end, that's when the pair joins together to form a larger black hole. That moment may be approaching for a quasar called OJ-287 at 3.5 billion light-years away. Flare-ups in the surrounding region have led astrophysicists to conclude that another black hole is flying around it. By measuring the giant's gravitational hold on its companion, astronomers estimate its mass at 18 billion solar masses. For a time, OJ-287 was the largest black hole ever detected. It no longer is. Deep in the heart of the Coma Galaxy Cluster, a mere 321 million light-years away, lies a giant elliptical galaxy known as NGC 4889. Astronomers used several large telescopes to measure the speed at which stars are orbiting around the center. They used that data to calculate the mass of the central object. A whopping 21 billion solar masses, give or take a few billion. Theoretically, there are no limits to how much weight a black hole can gain. And yet, even the largest black holes and their host galaxies seem to obey limits. What holds them back has to do with the way clusters of galaxies evolve, a pattern long noted by scientists. This computer simulation shows the evolution of a galaxy cluster in the early universe. The gravity of the entire region draws small galaxies by the thousands, along with great streams of gas into the center. So why doesn't the central galaxy and the black hole that resides within it capture all this matter? Why don't they swallow the entire cluster? You can see the answer in a region called MS-0735. At 2.5 billion light-years away, it appears in visible light to be a typical galaxy cluster. In X-ray light, you can see that it's enveloped in a cloud of hot gas, measured at nearly 50 million degrees. Hollowed out of this cloud are two immense cavities, up to 600,000 light-years across. That's enough room in each to stuff 600 galaxies the size of our Milky Way. Now add in a radio image of the cluster. You can see two vast streams of matter pushing out from the center. That's a giveaway that the cavities were formed by an eruption in the core of the giant central galaxy. Two jets shooting out of a central black hole have launched blast waves that plowed through the gas that makes up the intergalactic medium. The energy it took to carve out these X-ray cavities is remarkable. The equivalent of several billion supernovae, according to one calculation. In fact, MS-0735 has been referred to as the largest single eruption recorded since the Big Bang. It was generated by a black hole that weighs in at around 10 billion solar masses. Black hole jets like this have been seen all around the universe, including in our own cosmic neighborhood. This is the famous M87 galaxy, at the center of the Virgo galaxy cluster, around 50 million light-years away. Astronomers have been intensively studying the black hole that lurks in its heart. and recently estimated its mass at 6.6 billion solar masses. It powers a pair of high-powered jets that are plowing through the galaxy. But how does a black hole, a creature famous for hiding in the dark, emit this much energy? Think of a black hole as the eye of a cosmic hurricane, kept rotating by all the stars, gas, and other black holes that fall into it. As this matter flows in, it forms a spinning donut-like feature called an accretion disk, which works like a dynamo. The spinning motion of the disk generates magnetic fields that twist around and channel some of the inflowing matter out into a pair of high-energy beams or jets. How much energy depends on the black hole's gravity and how much matter has already crashed through the event horizon. Is this just another frightening spectacle of nature, or is it part of a more profound process at work? The largest black holes in the universe probably rose between 10 and 12 billion years ago, the age of the quasars. By releasing energy in the form of jets, they heated up their surrounding regions. This prevented gas from collapsing into the central galaxy and allowed smaller galaxies on the periphery to form and grow. But the impact of the black holes did not stop there. This Chandra image of the Hydra A galaxy cluster shows the same immense hot cavities glowing in X-ray light, as well as a jet blasting out of its central galaxy. Gas along the edge of the jet was found to contain high levels of iron and other metals, probably generated by supernova explosions in the center. By pushing these metals into regions beyond, a black hole seeded more distant galaxies with the elements needed to form stars in solar systems like ours. The black holes in these more remote galaxies then seeded their own environments. This is what might be happening in Centaurus A, also known as the Hamburger Galaxy. In X-rays, you can see a jet erupting from the center. Peering through the dense dust lanes that dominate our line of sight, astronomers have come to believe that it's actually two galaxies in the act of colliding. This computer simulation shows the effect of such a merger on black holes. As the two galaxies pass by each other, the pull of gravity disrupts their spiral shapes, forcing huge volumes of gas into their cores. As the black holes begin to feed, they emit blast waves that push much of the loose gas out beyond the boundaries of the new galaxy. In the final steps of this cosmic dance, the two black holes merge and emit one final blast. To think that our Earth, our solar system, ourselves, are the beneficiaries of these faraway monsters. The largest black holes have played dual roles in a great cosmic struggle. They are the product of gravity's relentless inward pull, the force that has drawn matter into galaxies, clusters. And the structures they form. But with their incredible power, they emit energy that pushes back on gravity. In so doing, these strange and powerful objects have become the master architects of space and time.
To the broiling heat of Earth's closest neighbor, radical weather is the norm in the solar system. We do have our own extremes here on Earth, but they pale in comparison to the fastest, dustiest, wettest, and most brutal alien storms. On Earth, the sun drives our weather, and sometimes drives it wild. When hot and cold collide in the atmosphere, watch out. This is true locally and globally. But storms on other planets are bigger, badder, and stranger than their counterparts on Earth. Why is that? Because of the sun? If not, what else fuels their fury? The basic laws of nature, the rules of the game, are pretty much the same wherever you go in the solar system. But every planet has its own way of playing the game. Right now on Mars, the entire planet is being covered in dust. This global dust storm blocks 99% of the sun's rays from reaching the planet's surface. It's actually a system of smaller but still massive storms churning dust high into the atmosphere. Once it starts, it takes months for Martian skies to clear.
Mars is just the most dramatic weather in the solar system in some senses. It's very rare in the solar system you get a weather event that can take out the whole planet.
So if the basic rules of hot and cold are the same on Mars, why is the weather so different from Earth? For one thing, Mars is half the size of Earth. It's also 50% further from the sun, so it's much colder. The average temperature on Mars is minus 80 degrees. That's almost 130 degrees colder than Earth. And the atmosphere is extremely thin and composed mostly of carbon dioxide. But perhaps the most important difference is this: Mars is a global desert.
What would Earth be like without water? Well, it'd probably have a lot of dust.
There's no liquid water at the surface of Mars, and there's very little water in the atmosphere, and so there's nothing to sort of keep the dust down.
On Earth, dust storms are localized and short-lived.
The reason for that difference in scale is that the storms are generating their own weather on Mars, whereas on the Earth, they're slave to the weather that's going on around them.
In other words, on Earth, the global weather system creates dust storms. On Mars, the storms create a global weather system. Astronomers have always been able to see big Martian dust storms easily with Earth-based telescopes. But what they couldn't see was what caused them. That would require a trip to Mars itself. In 2003, NASA landed 2 rovers called Spirit and Opportunity on the Martian surface. Their mission? To learn more about the geology of the red planet. NASA engineers always assumed that as these 2 vehicles roamed the Martian surface, dust would build up on their solar panels.
If you have a lot of dust that's falling down out of the atmosphere and coating the panels, pretty soon you're not getting much sun to the silicon. And in fact, we thought that was what was going to kill the rover Spirit and Opportunity.
Only it never happened. The rovers didn't die as expected. As dust built up on the panels, somehow something would clean them off. But how could this be? NASA engineers were baffled until the rovers themselves saw the culprit. Martian dust devils.
It turns out that dust devils were sort of our white knight. They came along and cleaned off the solar panels just at the time we were expecting to start having some problems.
There are beautiful photos that actually show dust devils moving across the Martian atmosphere and ghostly soldiers moving out there in the distance.
A dust devil is really an extreme form of rising hot air or convection.
And that hot air wants to go up, and it comes up just like, water going down a drain. Well, this is air that just spirals up into the colder parts of the atmosphere.
Whenever warmer air, which is less dense, rises up through cooler air, which is more dense, it rotates as it swirls upwards. Convection can be very powerful, strong enough to lift things up. On Earth, it lifts moisture, and that's how thunderstorms form. But on Mars, there is no moisture, so it lifts dry, dark dust and creates giant dust storms instead. Once airborne, Martian dust clouds absorb sunlight and heat the atmosphere. This supercharges the convection, lifting still more dust.
That produces more winds, which bring up more dust, and these things can spread up to thousands of miles across, or even, in some cases, they can envelop the entire planet.
And because the Martian atmosphere is so thin, it doesn't take much to get this cycle going.
You get a lot more difference between the surface temperature and the air temperature, and so the convection on Mars is very much more vigorous.
As a rule, Earth doesn't get the temperature extremes that Mars does. But sometimes, here and there in the deserts of Earth, convection can be very Martian-like. And we get dust devils, too. But at Arizona State University, Lynn Necrace makes dust devils to order in a lab to study them up close. He uses a vortex generator and substitutes lighter, dry ice for dust. What he creates is not an exact replica of how real dust devils form, but good enough to see how they pick up dust and debris.
Natural dust devils usually form from the bottom up, as opposed to tornadoes, which form from top down. So what happens when we turn this on, we have the airflow starting, and as the airflow starts to rotate from the fans down to the floor, we actually end up having the vortex form.
In other words, the vortex generator, basically a huge vacuum cleaner, imitates the swirling action of convection.
You can see here there's a wider base where larger particles of the dry ice are being swept up and gets wrapped up and tightens as it expands upward. The center of the core is where the majority of the lifting would occur.
Martian dust devils have been helpful, keeping the rovers clean. But could they actually be making a mess of the rest of the planet? Some scientists think there are so many at any one time, and they lift so much dust into the atmosphere, that together they trigger these much larger dust storms.
It starts wind patterns, and the air's warmer over here, and it's colder over here, and the air starts moving around. Pretty soon you're spreading dust over the whole planet.
And we found measurements that indicate there's up to maybe 200 dust devils per square mile per day during some parts of the summer.
And they can range from a couple of 100 feet tall to devils that stretch 6 or 7 miles high.
You can get just towering monsters of dust devils that we would never see on the Earth. The kind of maximum-sized dust devils you see on Mars are more like tornadoes on the Earth, where they're going up almost 10 kilometers. So these things are just real monster systems.
Back at Arizona State University, scientists blow crushed walnut shells as silicate particles in the Planetary Geology Wind Tunnel. to replicate dust and wind conditions on Mars.
If we can understand and sort of replicate what's going on, then we can, in a sense, understand how the Martian surface has been changing and continues to change as time goes on.
Oddly enough, their studies reveal that it's easier for winds to loft larger sand particles into the air than smaller dust particles.
This is because there's cohesional forces and static forces between the very small, fine dust grains. We imaged the rover deck and actually found that sand seemed to have bounced onto the solar panels, and we can see the skip marks across the surface. And this is interesting because we don't usually see sand typically reach that high.
Dust devils on Earth never have the punch to produce that kind of chaos here. Lucky for us. But what would happen to Earth if a giant Martian-style dust storm did overtake us?
If you had dust storms of Martian size on the Earth, you would find your city being enveloped in an orange-tan haze.
Air quality plunges as the storm churns. Dust blots out the sun, shutting down photosynthesis. No plants, no food. Temperatures would plummet. 65 million years ago, an asteroid may have struck the Earth, creating these same conditions, wiping out the dinosaurs.
It's not going to happen on the Earth, though, because there's going to be rainfall and moisture condensing on the dust grains and so forth and dropping them out of the atmosphere. So it's very hard for something like that to spread in the climate conditions that we have on Earth.
Forecasting Martian weather may someday be just as important as forecasting the weather on Earth. If we ever want to send a manned mission there,
the word environment no longer really applies just to the meadow next door and the little stream down at the end of town. It's the whole inner solar system. I mean, that's really our environment now.
The sun's energy bathes all the planets. On Earth, it creates hurricanes. On Mars, planet-wide dust storms. But with almost no solar energy, distant Neptune produces violent and powerful winds. Where do they come from? And just how bad are they? If Neptune's winds were to travel to Earth, these alien storms would literally blow us away. The orbit of Neptune lies 3 billion miles from the Sun, at the outer edge of the solar system. There's a lot we don't know about this big blue planet. Neptune's jet stream winds blast as fast as 1,500 miles an hour in its upper atmosphere. But how? The sun controls the weather on Earth and Mars, but it barely reaches out here. No sunlight means freezing temperatures, an average of minus 392 degrees Fahrenheit. So if there's no sun and no heat, where do these incredible winds come from?
One of the interesting puzzles is that as you go further out in the solar system, you get further from the sun, the winds don't go down. You still get very strong winds.
The energy for Neptune's winds must come from somewhere, and scientists are working to figure it out.
Neptune's energy is certainly not going to be powered by solar radiation. In fact, the energy we detect coming out from the planet in the infrared as heat is 2.5 times the energy coming in from the sun.
So the planet is creating its own heat, not from its core, which is made of rock and ice, but wrapped around this icy center is a mantle of ammonia, methane, and water, all being squeezed by enormous pressure and generating tons of heat. So while Neptune is frigid on the outside, on the inside it's giving off a lot of heat. This heat may help generate Neptune's winds. but they're still too strong to come from the mantle alone. Something else is pushing them faster and faster. Earth has a hot core too, and it's a lot closer to the sun. So why don't we have winds like Neptune? For one thing, our oceans store and release energy, and that helps generate our weather.
It adds energy in places, takes it out in others, in a very complicated system.
This complicated system produces a lot of wind. And just where are Earth's fastest winds found? Surprisingly, not over the ocean. They blow instead over the top of a fairly modestly sized mountain. New Hampshire's Mount Washington.
The highest winds ever observed by human beings were right here on Mount Washington at 231 miles an hour on April 12th in 1934.
Mount Washington Observatory, a private non-profit scientific institution, is responsible for tracking the weather and climate atop the 6,288-foot tall mountain. This remote weather station, accessible only by snow tractor in the winter, has kept daily records for the last 76 years.
It's definitely one of the most extreme locations on the planet. We regularly see in the wintertime winds exceeding 100 miles per hour every few days.
Nowhere near as ferocious as Neptune, yet still pretty strong. But why does this mountain, 1/5 the size of Everest, produce such fierce gusts?
We're at a place where we have winds converging from various directions, coming from the Ohio River Valley, coming down from the St. Lawrence River Valley, coming up the eastern seaboard, all converging here in this area on top of Mount Washington.
The elevation change from the valley floor to the summit of Mount Washington is very significant for any mountain range. It's over 4,000 feet, so air is forced to go over the mountaintop and forced to squeeze in there, and is accelerated as it's squeezed over the mountaintop.
And they measure it every hour, on the hour, 24 hours a day, 7 days a week.
It's blowing over 100 out here right now. Ice is forming on the instruments more quickly. It's time to go up and de-ice the instruments, even though it's blowing over 100. We got to do it every hour now.
Ironically, Earth's uneven surface, which channels winds into powerful gusts on Mount Washington, ultimately knocks them down over time. And this is the big difference between weather on Earth and weather on Neptune. Earth has mountains that slow winds down. Neptune is as smooth as a cue ball.
It's not so much a question of you're driving them stronger, because you're not. It's just that there's nothing to slow them down.
Simply put, once Neptune's winds get blowing, there's nothing to get in their way. So what would an average Neptune wind speed of 850 miles an hour do to us here on Earth?
We have parking level winds in the Earth sometimes above 100 miles an hour. We consider that pretty dangerous. So if we sat with 900 mile an hour winds from Neptune on the Earth, we would probably start wiping out everything on the surface and scraping everything off.
Giant Neptune takes wind and transforms it into something extreme and almost unrecognizable. But orbiting just beyond the rings of Saturn is a small moon that does the same thing to rain. This is Titan, where an everyday rain shower would turn Earth into an explosive fireball. It's a cloudy day, and a gentle rainstorm starts. Here on Earth, you'd grab your umbrella and consider it a minor inconvenience. But this isn't Earth, and it's no ordinary rain. You're on Titan, a small moon of Saturn, And in this chemical downpour, you'd need more than an umbrella to protect you. The rules of Earth weather definitely don't apply here. But Earth and Titan are alike in a lot of ways. On Earth, we have a solid surface, a protective atmosphere, and plenty of water. All these things make life on our planet possible. There's really nowhere else quite like Earth anywhere in the solar system. But Titan comes close. Like Earth, it has a solid surface. And that's not all.
Titan has an atmosphere that's, in general, very similar to Earth's. In some ways, it's mainly nitrogen like Earth's atmosphere. It's rich with organic material, also like Earth's atmosphere.
But similar isn't the same. Here on Earth, our atmosphere has a huge supply of water in it all the time, constantly evaporating and raining back down, like here on the Hawaiian island of Kauai.
Today we're on the slopes of Mount Waialeale, which is the cloud-shrouded mountain behind us. It rains over 40 feet a year here.
Earth's water cycle starts when warm, moist ocean air rises, forming clouds that eventually condense into rain. The rain falls back onto the land, where it eventually drains back into the ocean, starting the cycle again.
When water evaporates, it absorbs solar radiation. When water condenses, it releases all that energy into the atmosphere. And this transfer of heat helps to moderate conditions on Earth.
Earth's water stores as much as 80% of the sun's heat, helping keep our temperatures steady from the equator to the poles. Scientists theorize that Titan might have water or some other liquid that might produce a similar effect. And in 2004, when NASA's Cassini probe visited Saturn, it found some pretty good evidence to support that idea.
If you went to Titan and you were looking at the landscape, you would see something that in some ways would look almost familiar to you. You might see big mountains and valleys that were carved out by running liquids.
In fact, as Cassini flew past hazy Titan, its radar read the surface below. Scientists saw channels cutting across the surface, much like rivers on Earth do, some as long as 900 miles. The first strong evidence of liquid on Titan.
There are large bodies of liquid on the surface of Titan. Nowhere else in the solar system except for the Earth are there any large bodies of liquid.
Could water, the liquid that carves Earth's mountains and valleys, also be carving these features on Titan's surface? Or could it be something else? The problem is that Titan is too far away from the sun. If it was water, it would be frozen solid.
It's about minus 300 Fahrenheit on Titan, so things behave very differently on Titan than on Earth. Because it's so cold, methane, which is a gas on Earth, is a liquid on Titan.
One mystery solved. But just because methane is a liquid on Titan's surface doesn't mean it's part of a weather cycle like water on Earth. So how do we know that this methane also falls from Titan's sky? That answer is shrouded in mystery, literally.
Titan is completely covered in a thick haze of smog particles, like a very, very bad day in Los Angeles.
Despite the haze, the Cassini probe once again revealed the answer.
We can see the upper clouds, and we can see evidence for rainfall because the clouds drop very precipitously. We hypothesize that we're seeing the effects of rainfall.
Methane rainfall.
We think that Titan has methane monsoons, so we think that sometimes Titan has a lot of rain that is able to carve rivers and leave large fluvial deposits on the surface.
Cassini's radar imaging also revealed large methane seas on Titan's surface.
If you have liquid methane on the surface, in a lake, for example, that methane can evaporate off and become methane gas in the atmosphere. So you have kind of a cycling of methane between liquid phase and gaseous phase and between the surface and the atmosphere that's very similar to the water cycle that occurs on the Earth.
But methane is a flammable gas. So why isn't Titan on fire?
For any combustion, you need two things. You need both a fuel, which methane is, but you also need oxygen. And on Titan, you lack the oxygen. So the whole thing is basically a big fuel canister, but there's no oxygen with which to burn it, and so it's all very stable.
If it were cold enough here on Earth to produce methane rain, the oxygen in our atmosphere would create a worldwide firestorm. Luckily for us, that can't happen. Titan's methane cycle makes it both alien and familiar to us.
To me, Titan is very exciting because all the materials are so different, and yet these processes produce very similar landscapes to what we see on Earth.
Titan proves that where alien weather is concerned, looks can be deceiving. On Jupiter, it's all about size. Drop the Great Red Spot onto our world, and it makes even our worst hurricanes look like a breeze. This is the biggest and oldest storm in the solar system, and Jupiter's most famous feature. It even has its own name, the Great Red Spot.
It's about 2 or 3 times the size of the Earth, which makes it the mother of all storms.
We've known about the Great Red Spot in Jupiter's southern hemisphere for more than 300 years.
When Galileo invented the telescope, within a few tens of years, people had seen the Great Red Spot, and it's still there.
Familiar yet mysterious. Nobody knows how the Great Red Spot formed. But scientists are finally probing below Jupiter's cloud tops to uncover more about this enormous alien storm. The storm is powerful. With wind speeds of 300 miles per hour, it rises miles above the surrounding clouds. On Earth, we have storms that seem similar, though smaller and milder. Hurricanes. Also known as cyclones or typhoons, depending on where they form. They're our most destructive weather systems. But is there more than just a passing resemblance between Earth's cyclones and Jupiter's red spot?
When you look at the Earth from space at a hurricane, it's this big swirling pattern. It's round, it rotates. Jupiter's big storms look big and round and cloudy and they rotate, but there the similarity ends.
In a hurricane, there is an internal core, which is called the eye of the tropical cyclone, and that's a region of very calm winds and no clouds, and usually has a size of about 10-20 kilometers in diameter. And then away from the eye, there is the eye wall. Those are really cloudy regions with a lot of rain. And as you move outward, there is a whole region of about a couple of 100 kilometers with very, very strong winds and very strong rain.
Hurricanes draw power from heat in our oceans. But Jupiter has no oceans, and the sun isn't close enough to power a storm as big as the Great Red Spot. So where does it get its strength? Part of the answer is Jupiter's size. It's the largest planet in the solar system, almost as big as all the other planets combined. This mass generates a very strong gravitational pull, which in turn creates interior heat that rises to the surface. Another piece of the puzzle may be Jupiter's hypersonic rotation. Despite being much larger than Earth, Jupiter's day lasts only 10 hours. In other words, it spins incredibly fast. Could energy from this dizzying spin feed the Great Red Spot?
The weather is really dominated by this fast spin. There's shearing between different latitudes, and that shearing, plus a lot of heat that comes up from the interior of this very massive object, 290 times the mass of the Earth, leads to very violent storms.
Both Jupiter's and Earth's storms spin around in a familiar spiral shape. On Earth, it's because of an effect called the Coriolis force.
I'm sitting at the North Pole, and I want to throw a ball down to a friend who's in Los Angeles. And so if I threw the ball in that direction, the Earth rotates, and the ball will end up in the middle of the Pacific rather than in Los Angeles. So it's like if the trajectory was deflected to its right. And that's what we call the Coriolis force.
This force spins storms clockwise in our southern hemisphere. But there is a stark difference between Earth and Jupiter. The Great Red Spot is in Jupiter's southern hemisphere, and yet it spins counterclockwise. This is because of some other powerful winds.
It's bounded by jets, which are moving in opposite directions. And so like a cog between two conveyor belts, they're just feeding energy and momentum into the system.
Jupiter's complex jet streams spin the storm into organized chaos. But the greatest difference between Jupiter's red spot and our storms may be Earth's solid surface. Once a hurricane hits land, it comes apart pretty fast.
Where they come over land or over mountains, their behavior is very different from where they form over the oceans, and over warm oceans in particular, where we get hurricanes. And on Jupiter, there's obviously no solid surface.
With no land mass to stop it, the Great Red Spot just keeps on spinning and spinning and spinning. Scientists hope to learn more about our weather by continuing to study the storm.
On Earth, there's a limit to how far ahead you can predict the weather. On Jupiter, we can forecast where the red spot is going to be months in advance. It's practical value to understand what makes weather on Earth so unpredictable, and aspects of the weather on Jupiter are much more predictable.
Unpredictable or not, Earth's weather never gets as violent as on Jupiter. That's lucky for us, because if we shrank the Great Red Spot down to fit on Earth, we'd be in for disaster.
On the Earth, we go up to Category 5 hurricanes, let's think about Category 10 hurricane here. Not much would be left.
Alien storms are vastly different everywhere you go in our solar system. Even our next-door neighbor, Venus. They say we're sister planets. Lucky the resemblance doesn't include weather. Otherwise, we'd get seriously burned. Venus may be our nearest neighbor, but somehow its weather is radically different from ours. The second planet from the Sun is a cross between a toxic waste dump and Death Valley, but even worse.
So it's almost a planetary definition of hell.
The temperature is 900 degrees Fahrenheit. The pressure on the surface is the same as half a mile below the Earth's ocean. And if that's not enough, the upper atmosphere of Venus is choked with sulfuric acid clouds and winds clocked at 250 miles an hour.
To get a comparison for Venus, the best thing to do is climb inside of your oven and crank it up. And then in terms of pressure, you're talking about deep sea diving. It's like nothing. There's nothing comparable on the Earth. It's just a very, very extreme object.
On Venus, there's just no escaping the heat.
If you built up a hot spot on Venus, the massive atmosphere would just carry that heat away and spread it around.
But Venus shines so brightly in the night sky because its thick clouds reflect almost all the sunlight it receives. In fact, some early scientists assumed Venus would have moderate Earth-like temperatures.
When we went by Venus in 1962 with a spacecraft, we thought we would find a surface at 90 degrees Fahrenheit, sort of like Miami, Florida.
We were dead wrong. Something else must be at work on Venus. But what? So why doesn't Venus cool off the same way Earth does?
On the Earth, for example, we have sunlight coming in, hitting the surface of the Earth. Earth warms up a little bit, but the oxygen and the nitrogen in the atmosphere don't impede the light, so when it gets released out in the infrared, it goes right through the atmosphere and leaves and goes into space.
But on Venus, the atmosphere is 97% carbon dioxide, giving a whole new meaning to the greenhouse effect.
It becomes very, very hard for the surface to get its energy out.
So Venus really taught us a lesson, that if you have a blanketing gas, a greenhouse gas, it can warm up the atmosphere tremendously.
But why does Venus have so much more CO2 in its atmosphere than Earth? The two have much in common. They're even called sister planets. They're almost the same size, have roughly the same amount of carbon, and billions of years ago, both had lots of water. But eons ago, their paths mysteriously diverged. On Earth, water fostered life.
The Earth has most of its carbon in life forms, in the trees and the animals. But if you took all that carbon that's in the near-surface rocks and burned it up or released it, you would then create an atmosphere very much like Venus.
Venus's close proximity to the sun made it too hot to sustain liquid water. Instead, its water evaporated into the atmosphere, trapping the heat deposited by the sun and creating a runaway greenhouse effect. Once in the atmosphere, the water molecules were exposed to solar ultraviolet rays that broke the molecules apart.
It really wasn't recognized by the scientific community how important the greenhouse effect was prior to going by Venus and seeing this amazing place where it was 900 degrees Fahrenheit and not 90.
It took several doomed missions to Venus to figure it out. Starting in the 1960s, both the United States and the Soviet Union sent unmanned probes past the planet and down to its surface. It didn't take long before Venus crushed and burned them. Then, in 1981, the Soviet lander Venera 13 set a record for survival on the surface of Venus. 2 hours and 7 minutes. It was able to take pictures and samples of the surface before being overcome by the heat.
You're sitting there with this 900 degrees Fahrenheit heat all around you. It's going to get in there and bake you after a while.
Scientists one day hope to send a probe to Venus that can survive its hellish environment, to help us confirm our theory of how this planet went astray. Because if circumstances were just a little different, our sister planet might just be our twin. Remove our atmospheric shield, and you're on the road to hell.
As soon as you're heated up to something like 400 degrees or so, you'd probably start getting some smoldering smoke, and way before it hit the 900 degrees, the Earth would burst into flames because of all the oxygen around.
Once the oceans boiled away, the carbon locked in rocks on the ocean floor would cook, and over millions of years re-enter the atmosphere.
Probably if you came back to the Earth system after this happened, you'd find a planet looking much like Venus.
We're a long ways away from such a drastic change, but it's sobering to look at Earth's sister planet when the sister planet went on a very different track than we did.
So cosmic forces turned Venus into a planetary barbecue. But on this violent, stormy world, time and the elements have produced some of the strongest thunderstorms ever measured. Welcome to Saturn. lightning cuts the sky. This violent weather system grows bigger than the entire United States as it pummels the atmosphere with the most powerful lightning ever seen. Except this lightning can't be seen, because these bolts are electrifying the skies over Saturn. Despite the raw power of Saturn's lightning, scientists have been unable to see it, partly because Saturn's rings are too bright.
The rings are so bright, if you were on the night side of Saturn, it would be considerably brighter than the Earth under a full moon.
But Saturn also hides its lightning within thick, choking clouds of ammonia.
It's probably 100 kilometers down that the lightning is happening, and that complicates seeing the lightning flashes.
But the lightning is there, and scientists know it because they've heard it. Radio wave detectors on the Cassini orbiter have recorded the sound of Saturn's lightning.
We can hear the static of lightning just as you could with an AM radio going down the highway on Earth.
And this static reveals the power of the lightning that we can't see.
You can measure the energy in those radio waves and compare it with the energy that your radio picks up when there's a thunderstorm around on Earth. And the Saturn ones are big. They're more powerful, maybe 100 times.
And Earth's lightning can help scientists understand how storms work on Saturn. Within Earth's storm clouds, just like in Saturn's, updrafts drive moisture higher, causing ice to form. These ice crystals rub against each other, take on a positive charge, and become attracted to negatively charged water droplets lower in the cloud. This sets the stage for a potentially powerful discharge of energy.
Once you get that charge separation that builds up so intensely that some theorize that it can be as strong as 100 million volts, that the cloud then must release that energy.
On Saturn, the same thing happens on a much larger scale. In fact, the lightning is 100 times stronger than Earth's. That's a staggering 10 billion volts of electricity. Thunderstorms in Saturn's southern hemisphere span thousands of miles and can last as long as a month. But scientists aren't sure what makes Saturn's storms bigger and longer lasting. It could be Saturn's supersaturated atmosphere.
Probably the fact that there's more water in the atmosphere, pound for pound, on Saturn makes the storms bigger.
More water droplets means more friction, which means bigger lightning bolts. But energy emerging from the planet may also contribute to the power in Saturn's thunderstorms.
It turns out that where Lightning Alley is on Saturn is a place where the winds are flowing the slowest. If you go deep down in the atmosphere, you'll see the same winds as you do up high. It's a place where the energy being released deep down below can make it on up to the upper atmosphere without being sheared apart, and allows storm systems to be organized.
Earth's atmosphere isn't built that way. So, as violent as our storms get, they're nothing compared to the systems on Saturn. Even a run-of-the-mill mega thunderstorm on Saturn would devastate us here.
A Saturn-sized thunderstorm on the Earth would mean a thunderstorm that grows to cover all of North America and presumably has very strong winds and rain. This is something that's unprecedented on the Earth.
Saturn's hyper-violent thunderstorms are proof that our planetary neighbors have weather far more ferocious than ours. But the laws of physics that create Saturn's storms are the same laws that create our own weather. Massive dust storms, unrelenting winds, killer lightning, powerful hurricanes, and searing heat.